Have you ever just stopped for a second and really thought about what's happening inside your head? I mean, right now. It's not just your thoughts, it's the whole show. The colors you see, the sounds you hear, the entire feeling of reality around you. All of it is being built from scratch, moment by moment, by the most complicated thing we know of in the entire universe.
And that's really the big question we're tackling here. How does this 3-pound organ sitting inside your skull, which you can't even feel working, manage to generate your entire conscious experience? It's a biological machine that somehow turns raw electricity and chemistry into you. So how on earth does it pull that off?
To figure it out, we're going to go on a journey from the bottom up. We're going to start super small, with the individual cells themselves, the building blocks. Then we'll see how they talk to each other, using this wild electrical language. From there, we'll see how those conversations build circuits, how those circuits create these amazing functional maps in your mind. And then, the grand finale, how the whole system can literally change itself based on your experiences. Let's dive in.
All right, section 1. To understand the whole machine, you've got to start with the smallest parts, right? So let's look at the actual cells that make this all possible.
You know, for a long time, scientists were in this huge debate about what the brain was even made of. One camp, with their reticular theory, thought it was all just one big, continuous web of tissue, like a giant net. But then this guy, Santiago Ramon y Cajal, came along, and get this, he used his rival's own staining techniques to prove the exact opposite, the neuron doctrine. He showed that the brain is made of countless individual, separate cells, and he was right. Realizing the brain was a network of individuals, not just one big blob, completely changed everything. It opened the door for all of modern neuroscience.
And that individual cell? It's the neuron. This is the star of our show. Absolutely everything you think, everything you feel, everything you do, it all comes down to these incredible little cells receiving, processing, and passing along information. They are the fundamental unit of your mind.
But you know, no star works alone, right? Neurons have this amazing support crew called glial cells. You can think of astrocytes as the backstage crew. They're making sure the chemical environment is just perfect for the neuron to do its thing. And then you have oligodendrocytes, who are like the expert electricians. They wrap some of the neuron's wires in this fatty stuff called myelin, which makes their signals travel ridiculously fast. Seriously, without the glia, the whole show would grind to a halt.
Okay, so we've got our cast of characters. We have the neurons, and we have their support crew. But how do they actually talk to each other? Well, it turns out they speak a language unlike any other, a language of pure electricity.
Now, a neuron that's just hanging out at rest isn't really off. It's more like a tiny, charged-up battery. There's this negative electrical charge of about negative 70 millivolts across its membrane. That negative charge means it's polarized. It's holding on to a bunch of potential energy, like a coiled spring, just waiting for the right trigger to be released.
And when that trigger hits, bam, you get this, the action potential. This is the spark. This is the message. It's this super brief, really dramatic spike of electricity that just zips down the neuron's axon. And here's the key. It's all or nothing. That means it either fires at full strength or doesn't fire at all. There's no in-between, no kind of sort of firing. It's the brain's version of a 1 or a 0.
So how does this little electrical domino effect actually play out? Well, it's this incredibly fast 4-step dance. First, you're at rest, sitting at that negative 70 millivolts. Then, when it's go time, tiny gates for sodium ions fly open, and all this positive sodium rushes into the cell. That makes the voltage inside shoot way up. That's the rising phase. Then, just as fast, those gates slam shut and new gates for potassium open up. Now, positive potassium ions rush out of the cell, causing the voltage to drop back down. Finally, this little molecular machine, the sodium-potassium pump, gets to work, tidying everything up and pushing the ions back where they started, getting the neuron ready for the next signal. All of this happens in a few milliseconds. It's amazing.
So, we've seen how a signal can zip down one single neuron. But let's be honest, the real magic, the whole point of the brain, happens when that signal gets passed from one neuron to the next. And this happens through something we can think of as a synaptic handshake.
That handshake takes place at the synapse. It's this teeny, tiny gap between two neurons. But here's the twist. That electrical action potential, that spark, it can't jump the gap. It's like a river it can't cross. So to get the message across, the neuron has to do something clever. It converts the signal from electrical to chemical. It releases these little chemical messengers called neurotransmitters, which just float across that tiny gap to the next neuron.
Okay, so how does that next neuron actually hear this chemical message? It's got specialized docking stations called receptors, and there are two main flavors. Ionotropic receptors are the fast and direct option. A neurotransmitter clicks in and bam, a channel opens right away. It's like a key turning a lock. But then you have metatropic receptors. These are more indirect. It's more like ringing a doorbell. The neurotransmitter binds, and that kicks off this whole chain reaction inside the cell, which then eventually causes a response. It's slower, sure, but it allows for much more complex, fine-tuned conversations between cells.
So we have our neurons, and we have the synapses connecting them. Now let's zoom out, because when you connect billions, and I mean billions, of these simple little components together, you get the most powerful computer on the planet. You get a neural circuit.
So how does just one neuron in a circuit make a decision? Well, you have to picture it getting bombarded with thousands of messages from other neurons all at once. Some of those signals are excitatory. They're like go votes, making it more likely to fire. Others are inhibitory. They're the stop votes. And the neuron's job, its entire existence, is to constantly add up all those votes. If the go signals outweigh the stop signals by enough to cross a certain threshold, it fires its own action potential. That's it. That is the fundamental calculation of the brain happening billions of times a second.
Now, what's so cool is that all these circuits performing all these tiny calculations aren't just a random jumble of wires. When you zoom out to an even bigger scale, you find that they are beautifully organized into functional areas, creating a literal map of your abilities right there in your brain.
We've known about this for a long time, actually, thanks in large part to studying patients with brain damage. It's these tragic cases that show us how specific abilities are tied to specific places. For example, damage to a spot called Broca's area can lead to Broca's aphasia. A person knows exactly what they want to say, but they really struggle to produce fluent speech. But damage to a different spot, Wernicke's area, can cause Wernicke's aphasia. They can speak just fine, fluently even, but the words are jumbled and don't make any sense, and they can't understand language either. Two different spots, two totally different jobs. The brain is organized.
This localization gets even cooler. Your brain literally contains a map of your entire body. It's called a somatotopic map. But here's the fun part. It's not a proportional map at all. It's completely distorted, based on what's most important. Body parts that need high sensitivity and fine motor control, like your hands and your lips, take up a massive amount of brain real estate compared to, say, your back. It's a map that shows what's most important for how you interact with the world.
And that brings us to our final section, and honestly, maybe the most profound idea of them all. This unbelievably complex organ, with all its cells and circuits and maps, it's not a finished product. It's not fixed in stone. It is alive, it's dynamic, and it is constantly, literally rewiring itself based on your life.
The tragic but incredibly important case of patient HM taught us so much about this. To treat his severe epilepsy, surgeons removed parts of his brain, including a structure called the hippocampus. And while it cured his epilepsy, HM was left completely unable to form new long-term memories. He could remember his childhood perfectly, but he couldn't tell you what he ate for breakfast that morning. His case was the first real proof that specific parts of the brain are absolutely critical for turning our day-to-day experiences into lasting memories.
So how does that actually happen down at the cellular level? It happens through a process called long-term potentiation, or LTP for short. And the idea behind it is actually pretty simple, but it's so powerful. When one neuron helps another one fire, over and over again, the connection between them, that synapse, gets physically stronger and more efficient. As you can see here, the response after this strengthening is way bigger. This is the physical trace of a memory being formed. That old saying, neurons that fire together, wire together, it's literally true. Your experiences are physically sculpting the connections in your brain every single day.
Which, of course, brings us to a pretty mind-bending final thought. We've gone all the way from a single cell to this vast learning network. The brain you have in your head right this second is physically different from the one you had when you started this explainer, because the act of learning this has changed it. So if the very hardware of your mind is always in flux, being shaped by every single thing you see and do and think, are you really the same person you were yesterday?